and the analytical. Welcome to mine and George's presentation on lead as a water contaminant and the analytical steps to deal with it. So the reason we chose this topic is because lead poisoning is prevalent across the world, but mainly in developing countries. Lead poisoning can obviously lead to death, many organ failure, and it can lower the IQ in children. Lead poisoning equates to 1.5% of all global deaths, and it cost, for example, Africa a total of 4.03% of their total GDP, as opposed to the EU, which is only 0.31%. So context. So first of all, I'm going to talk about the background and the symptoms. So like I said, children are a lot more exposed to lead as they absorb 4 to 5 times the amount that adults do. This is due to growing bones and organs. Children, it can lower their IQ and cause behavior disorders. And in adults, then for prolonged exposure, it can cause organ failure. No amount of lead in the body is safe. Up to 5 micrograms can cause a drop in the IQ, which I'll be talking about more later on. So why is this a problem? Well, in the UK, it's not a massive problem, and it hasn't been for the last 40 to 50 years, due to laws coming into place with things like lead in fuels and lead in paint. And however, there is still a problem in a sense in the UK with lead piping. Some households still have old lead piping, which can contaminate drinking water, which would lead to acute lead poisoning. But like I said previously, any amount of lead within the blood is a problem. However, in developing countries, so lower to middle income and upper middle income countries, you can see that they have a much higher rate of DALYs, which is disability adjusted life years, which is the number of years spent disabled or dead because of an illness, and in this case it's lead poisoning. So the death rate has increased by 21% from 1990, and obviously as the world has got a growing population, the need for lead has increased, therefore the death rate's increased. However, the high income countries' death rates have declined by 30%, which tells us that obviously the countries that are getting the death toll are countries with poor law enforcement with regards to lead in things like paint and fuels, and poor waste disposal and worker health. So 92% of the deaths are from low and middle income countries, as you can see from the graphs. Here we can see that that lead exposure can lead to IQ drop. Just 5-point drop in IQ leads to a 57% increase of a population with intellectual disabilities, a decrease of more than 50% of population with exceptional intelligence, and then one unit of lead in your blood can cause social problems. As you can see there, 6.5 to 7% of boys and 6.4 to 9.3% of girls got suspended with higher lead in their blood. So like I said, in developing countries, lower IQ with their population means that those countries will struggle to get out of the loop of industrialization, and they'll struggle to breach the border of high income countries. Again, the social problems come into that same bracket. So definition of problem in terms of chemistry, what is the actual chemistry going behind it? So lead affects the calcium signaling, and as you can see by the diagram here, calcium, which would come the anomaly, is getting blocked by the lead, which means that neuron signaling is blocked. Lead can bind to biological molecules, such as amides and different enzymes, and it can alter their configuration. And like we said previously, these processes inhibit major functions to do with neurological development in mainly children. So solutions. Here you can see a graph of where lead is banned in paint. And here you can see a graph of where lead is the highest pollution levels. As you can see from the graph straight away, the highest leaded pollution correlates to where there is no laws, so mainly Africa. So obviously banning lead in paint, petrols, and other day-to-day items is a major factor to solve this problem. We also have in the UK, like I said, lead piping. So if you test for lead piping, you can scratch it because it's a soft metal. It'll reveal a shiny layer and you can get them changed. You can also use EDTA, which binds to the lead within your blood and then will remove it. A modern solution then would be if lead is in a water supply, they can use these microbots. The outer layer is made of graphene, which captures and binds the lead to the surface. The inner layer of platinum decomposes hydrogen peroxide and allows these microbots to propel through the water for self-sustain. And then the middle layer of nickel allows for magnetic control, so they can be pulled out of the water by a magnet and then reused. From that graph there, you can see that 1,000 parts per billion of lead went down to below 50 parts per billion of lead in 60 minutes. So these microbots are obviously fantastic and, like I said, recyclable. So you get the lead back and the microbots for reuse.
We will now take a look at the role of analytical chemistry in solving the problem of lead contamination. First of all, we need to identify how much lead is contaminating our given sample, whether it's a lake or a test tube. And this works through inductively coupled plasma, optical emission spectroscopy. And as I said, it's all about finding how much is there, then how far do we have to go, what's the best technique in order to get there. We have analytical chemistry playing its role in surface chemistry with regards to the kinetics and thermodynamics of the interactions between the surface and the lead-2+ ion. What is a good material? What is the best conditions for such a material? Now we will look at working principles, as we actually need to understand how our roles work. We take ICP OES and we can find lead in samples of trace value of up to 0.1 parts per million, which is listed here. Now we have different methods of ICP, such as AES and mass spec. Mass spec you can get down to about part per billion, but we don't need to worry about that today. What we need to know is, how does this ICP OES actually work? Well, we heat the sample with a flame torch, then put through an electromagnetic coil that surrounds the plasma which it hits, which is an argon plasma heated about 10,000 Kelvin. The ions fire at the side. There will be a detector here, and this will be able to detect the amount of lead ions among other metal ions. We can test for many at the same time, which is what makes this method so good, because we might think there's a lead contamination, but there might be something like arsenic or anything else in there. But of course we're considering lead, so we'd want to know how much lead's in there. Next, we must consider the working principles of the surface chemistry. First, we'll look at the graphene microbots that have been previously mentioned. And as it's stated, they are magnetic. This makes them very easy for removal because we can put a magnet in, they'll stick to it. They are sometimes on gold wires that can be attached to those too. But if you then let them loose in a solution so they can all swim about, you can then just pull them back out again with a magnet and then drop them into some acid solution, normally nitric acid. You can recover your lead. It's very efficient, but you're looking at platinum, nickel, platinum, and graphene. Very expensive. So not for everyday practical use. When looking at the working principles, how do the lead-2 ions actually bind to our surfaces? Well, in the case of the graphene surface, the graphene is actually a graphene oxide. So it's a polar surface with hydroxyl groups and carbonyl groups. There are also some alkene groups which can interact with the lead-2 cation. These polar groups will be through the oxygen being polar and electronegative want to form interactions with the cation. And here we have a pi bond, and the negative pi bond will want to interact with the lead cations. Alumina, or Al2O3, is polar with polar oxygens, similar to the carbonyls and hydroxyl groups. This will make them bind into the alumina, and they will precipitate from solution. But one big thing, which is actually true for both of them, is that we need to consider the pH. And as a previous image shows, you want to use an acidic pH, or wash your microbots in acid to remove the lead, and you can use it for later. The alumina, well, you can see here that the gamma alumina is better throughout, but due to hydroxide interactions with the lead in basic pH, you want to use an acidic pH, as this will give you a better reuptake of lead to be. It's all well and good talking about these fancy solutions, but what are the actual impacting benefits? Why do we even bother? Well, we end up with less lead-related illnesses, especially in children, which means that they have less issues growing up. They can go to school. If you go to school, you can get a better job. You do more thinking. If you do more thinking, your country develops because more people come up with more ideas, and they make the world better. They make the environment better, which is a positive feedback loop. And as I said, if it makes the environment better with less contamination, children are less likely to get ill, the country develops, the environment gets better, it all feeds back. It's all very helpful to a country. Thank you for watching this presentation on why lead contamination of water is so important and why it needs to be fixed.